Hi, Algebra 2 girls. This is just a few extra examples if you're looking for a little bit more detail in how to do both function operations and function composition. So these are two additional examples that I'd hoped to provide for you in class today, but we just ran out of time. So you'll have one example that deals particularly with polynomial functions and then one that deals with rational functions. So if either one's feeling more challenging for you, you can certainly just jump down to the example that you need. So our first example, we are provided with these two different functions. F of x is equal to x squared minus 3, and g of x is equal to 2x plus 1. So this example should look pretty similar to the one that we started out with in class today. We have function operations first, so our basic addition, subtraction, multiplication, or division. And then we also have our function composition operations. So the addition and subtraction and multiplication should all feel very, very familiar for polynomials because it's the same kind of operations we've done with polynomials. So here where you're adding functions, we're just going to take the function that is x, f of x, which is x squared minus 3, and the function that is g of x, which is 2x plus 1, and we're going to add them together. And in this operation, all that you're doing is combining like terms. So we just have one quadratic, that's our x squared. We have one linear term, which is our 2x. And then we have to combine our two constants, negative 3 and positive 1, to get negative 2. So that's your final answer there. So function addition is the same thing as polynomial addition. It's just what you're putting together. Part B, we have g of x plus g of x. Well, our g of x function is just 2x plus 1. So we take that and add it to itself. So in this case, we have a 2x plus a 2x, which gives us a 4x. And then we'll have a 1 and a 1, which will give us a 2. Then we have some subtraction. So this one gives us f of x minus g of x. So that's just going to be our x squared operation minus our g of x operation. Again, we can't really do anything with the quadratic or the linear term, so we just have to write those out. But here we'll have negative 3 minus 1 more, so we'll end up with negative 4 at the end here. The last operation is multiplication, so we're going to multiply f of x, which is x squared minus 3, by g of x, which is 2x plus 1. So we're going to be foiling here. If we FOIL, we will end up with 2x cubed, and then we'll have plus x squared minus 6x minus 3. So that's our multiplication operation there. So all pretty straightforward for those ones. The next thing we want to be able to do is to identify the domain of any functions we encounter. So kind of what is the restriction on what x values we can evaluate the function at. And the nice thing about polynomials, so a linear expression like this guy here and a quadratic expression like this one here, is that we are able to evaluate those functions at any x point. So our domain is going to go from negative infinity up to positive infinity. And as we discussed today, there are a couple of ways to say that. So you can use inequality notation, you can use interval notation, or you can just say all real numbers as well, because you can plug in anything to those. That's all review. The new stuff is the function composition. So the first function composition operation we have here is that we are looking to evaluate f of g of x. So what that means is we want to take the entire g of x operation and substitute it in for x in the f of x. So what I recommend doing first, just to get started with that operation, is to rewrite the g of x in terms of whatever equation it is. So this is going to be f of 2x plus 1, because that's what g of x is. So then I just look at my f of x operation, and anywhere I see an x, I'm going to plug in 2x plus 1. So that will give me 2x plus 1, that quantity squared, minus 3. And from there I need to FOIL out. So I need to multiply 2x plus 1 times 2x plus 1, and then I need to subtract 3 from there. So this will give me, if I FOIL, 4x squared. My inner term will be 2x, and my outer term will be 2x. So that will be plus 4x, and then I'll have plus 1 minus 3 at the end. So if I combine my values, I'll have 4x squared plus 4x minus 2. So that's my function composition. Instead of plugging a number into a function like we're used to, we are just plugging in an entire function. So it's going to be a little bit bulkier than what we've seen before. That would be f of g of x. So plugging the function g into the function f. So now, let me just erase this here so we can consider it in the opposite form. We want to be able to identify both f of g of x and also g of f of x. So the next problem on this slide asks me to find g of f of 1. So one possible option is to start by fully evaluating g of f of x, and then to find that result at 1. So let's try it that way first. So we're going to compose g and f. So what that means is g of f, anywhere I see an x in g, I'm going to plug this whole thing in, so x squared minus 3. So this will be g of x squared minus 3, which, given the function that we're provided, will be 2 times x squared minus 3. And then I have a plus 1 at the end of f of x. So let me zoom out a little bit here so you can see the functions themselves. So I took this entire x squared minus 3, and what I did is I brought it over and replaced this x right here with that operation. So now I can distribute in here, and I'll have 2x squared minus 6 plus 1, which is going to be 2x squared minus 5. So what I was asked to do was to evaluate that operation at 1. So this is going to be 2 times 1 squared minus 5, or 2 minus 5, which will give me negative 3. So that's my final answer there. One of the things that we discussed in class today is that you can do function composition at a specific point, so at a numerical x value, by doing the function composition operation, which gets us to this new function, and then we just plug in the x value. So that's one technique. The other technique, I'm going to go ahead and erase the work that we just did and show you how we can do what I call the numerical evaluation technique, which means that you're not actually finding a new function, you're just plugging into the functions you already have. So with this operation, what I would start by doing is finding f of 1. So my f is this x squared minus 3, this whole thing up here. So I plug that in, and that's going to give me 1 squared minus 3, or 1 minus 3, which is negative 2. So the operation f of 1 is the same thing as negative 2. So instead of finding g of f of 1, I can find g of negative 2. So if I go to find, I'm sorry, I keep bumping the wrong button. If I go to find g of negative 2, what I'm going to do is look at my g function, which is that 2x plus 1, negative 2 for x, so I'll have 2 times negative 2 plus 1. And so that operation will give me negative 4 plus 1, which is negative 3. And again, that's going to be the same operation that we had before when we had evaluated the entire function by itself. So you can choose either path when it comes to function composition. So this was a polynomial example. Now I'm going to scroll us down to the next example, which no longer deals with polynomials. This operation has f of x is equal to 9x to the 1/3, and g of x is equal to 81x to the 1/2. So everything about this operation is going to go the same way that we saw with polynomials, but we're just going to have to use our operations with rational exponents and roots here instead of our polynomial rules. So here, first off, we have some exponent addition, or functions with exponents in their addition, because our first operation asks us to find f of x plus f of x. So my f of x is this 9x to the 1/3 power. So I'm going to take 9x to the 1/3, and I'm going to add another 9x to the 1/3. Now these are like terms, so I can just combine them together. 9 plus 9 is going to give me 18x to the 1/3. For g of x, the operation is going to be really similar. I have an 81x to the 1/2 plus an 81x to the 1/2. So if I add those together, I'm going to get 162x to the 1/2. So just combining like terms. Now the multiplication and division here is going to look just a little bit different. And the reason for that is at this point in time, we are going to have to use our polynomial operations, our exponent operations. And so when we use our exponent operations, we need to make sure that we are either adding if we multiply the exponents or dividing if we subtract them. So here we're going to be dividing, and this tells us to take f of x, which is 9x to the 1/3, and divide it by 81x to the 1/2. So first I want to take a look at the 9 and the 8, 81. So those two values can simplify to 1/9 because they're both divisible by 9. Then with my 1/3 and my 1/2, what I want to do is subtract. So I'll do 1/3 minus 1/2. But the issue here is that 1/3 and 1/2 don't have common denominators. So I need to change my 1/3 to 2/6 and my 1/2 to 3/6. So this will become a negative 1/6. So I'll end up with 1/9 x to the negative 1/6. And that negative here just tells me I need to move it down to the bottom. So I'll have 1/9 times x to the 1/6 power. So that is my division operation. Last up, I have some multiplication. So I need to take f of x and multiply it by g of x. So I'll have 9x to the 1/3 times 81x to the 1/2 power. So here, when I multiply 9 by 81, I'm going to get a bigger number. I'll get 729. And when I add 1/3 and 1/2, I have that same dilemma as before where I need to get it into a common denominator of 6. So I'll have 2/6 plus 3/6, and that's going to be 5/6 as the exponent on the x value. So I'll end up with 729 times x to the 5/6. Now the next operation asks us about the domain. So the domain, again, is just what x value can you plug into the function. So our first function, f of x, is equal to 9x to the 1/3. That's really the same thing as saying 9 times the cubic root of x if we converted it into root form. And so anytime you have an odd root like this is an odd root, you can also plug any x value you want in. So the domain here would be from negative infinity to positive infinity, or all real numbers. That function, I can take any positive number, any negative number, and I'm going to get a real valued result when I plug it in. The other operation, though, g of x is equal to 81x to the 1/2, is the one that's a little bit of an issue, because if I convert this to be a square root, I'm going to have 81 times the square root of x, and square roots are even roots. And the issue with even roots is that we can only plug in numbers that are starting at 0 or are larger. Anything smaller than that is going to give us a negative number, so it's not included in the domain. So here we can say that our domain goes from 0 to infinity, or we can just say that our x values need to be greater than 0. So all odd roots, we're going to have a domain of all real numbers. All even roots are going to start out at 0.